Good evening, students.
Good afternoon, sir.
Yes, good afternoon. So, without wasting any time, let us start with the discussion. Last class, we have been discussing about electrochemistry, electrolytic cells. After Faraday's laws, we have solved different examples. Let us continue with the different sets of examples and then proceed with the last concept. So, then this is the next example. 1 mole of Fe is deposited on electrode by passing X coulomb charge through FeCl3 solution. Then calculate weight of sodium deposited on passing same charge through molten NaCl solution. So there are two solutions, FeCl3. So 1 mole of Fe deposited, we know Fe plus 3 ions, FeCl3 gives Fe plus 3 chlorides. So Fe plus 3 will take up 3 electron to form Fe. From here I can write the equivalency condition, 3 mole of electron is equivalent to 1 mole of Fe. 3 mole of electron is equivalent to 1 mole of Fe. 1 mole of Fe is deposited on electrode by passing X coulombs. So 1 mole of Fe deposited means 3 moles of electron required. 3 moles of electron will carry 3 Faraday. That is 3 into 96,500 coulombs is equivalent to 1 mole of Fe. So this much charge you have passed. So that 1 mole of iron has been deposited. Now then calculate the weight of sodium deposited on passing same charge through molten NaCl. NaCl gives Na plus plus Cl minus, and Na plus will take up 1 electron to form Na. So from here I can write 1 mole of electron is equivalent to 1 mole of sodium, 1 mole of sodium. So how many mole of electron we have passed? Like 3 Faraday, 3 moles. So 3 into 96,500 coulombs will be equivalent to 3 mole of sodium. What is the atomic weight of sodium? 23. So 3 into 23, 69 gram. 69 gram of sodium is going to be deposited whenever you pass 3 Faraday of charge. That is 3 into 96,500 coulomb. Is that clear to everyone or not? Very simple.
Yes, sir.
Yes.
Yes, right. The current is passed through XSO4 and Y2SO4. XSO4 dissociates to give X plus 2 plus SO4 2 minus, because sulfate will have minus 2 charge. So whatever the cations you have, that should be neutralizing the charge of all the anions, that is plus 2. X should be in the plus 2 state. Whereas you get 2Y plus plus SO4 2 minus. The relative atomic mass of X and Y are given. Atomic mass of X is to atomic mass of Y is 2 is to 1. Atomic mass of X is to atomic mass of Y is equals to 2 is to 1. Determine the ratio of masses of X and Y deposited. The same current is passed. So we know X plus 2 electrons gives rise to X. So 2 Faraday should be equivalent to 1 mole of X, because 2 moles of electron means 2 Faraday. Similarly, you have Y plus will take up an electron to form Y. 1 mole of electron means 1 Faraday should be equivalent to 1 mole of Y. So 2 Faraday should be equivalent to 1 mole of X. 1 mole of X will be atomic weight of X. Same current is passed, so same charge. So 1 Faraday is giving 1 mole means 2 Faraday is giving how much? 2 mole of Y, that is 2 into atomic weight of Y. So weight of X, this is nothing but weight of X deposited. This is nothing but weight of Y deposited whenever you pass same current. So weight of X is to weight of Y is equals to atomic weight of X is to atomic weight of 2 into atomic weight of Y. Atomic weight of X is 2 times that of atomic weight of Y. That is 2 into atomic weight of Y is to 2 into atomic weight of Y. So that will be 1 is to 1. Because they have given atomic weight of X by atomic weight of Y is 2 by 1. So atomic weight of X is 2 times that of atomic weight of Y. Since the ratio has been given, I have substituted the same ratio. Got the respective ratio of masses deposited. That is 1 is to 1 is the exact ratio of masses deposited for the respective elements X and Y. Right. Let us proceed to the next question. 1 mole of electron passes through each of the solution like AgNO3, CuSO4 and AlCl3, when Ag, Cu and Al are deposited cathode, the molar ratio of Ag, Cu and Au deposited is how much? Molar ratio they are asking. We know AgNO3 gives what? AgNO3 dissociates to give Ag plus plus NO3 minus. CuSO4 dissociates to give Cu2 plus plus SO4 2 minus. AlCl3 dissociates to give Al plus 3 plus 3Cl minus. So Ag plus will take up an electron. Again from that equation I can write Ag plus will take up an electron to form Ag. Ag deposited. The molar ratio of copper, silver, copper and aluminium when 1 mole of electron is passed. So 1 mole of electron is equivalent to 1 mole of silver. 1 mole of Ag. Similarly, I can write Cu plus 2 electron gives us to Cu. So 2 moles of electron is equivalent to 1 mole of copper. So 1 mole of electron will be equivalent to half mole, 1/2 mole of Cu. Similarly, we can have AlCl3, that is Al plus 3 electron gives us to Al. So 3 mole of electron is equal to 1 mole of aluminum. So 1 mole of electron is equivalent to 1/3 mole of aluminum. Yes or no? Therefore, number of moles of silver is to number of moles of copper is to number of moles of aluminum is equals to 1 is to 1/2 is to 1/3. Multiply throughout it 6. 6 is to 3 is to 2. Option 2 is the right option. Is that clear or not, students?
Yes, sir.
Yes, sir.
Right, very good. An electric current of 100 amps is passed through a molten liquid of sodium chloride for 5 hours. Calculate the volume of chlorine gas liberated at the electrode at NTP. So molten sodium chloride. So NaCl gives Na plus plus Cl minus. And we are talking about chlorine gas. So because NaCl is a molten, so only Na plus and Cl minus ions are there. So 2 Cl minus will be giving chlorine gas and 2 electrons are lost. 2 Cl minus ions will generate Cl2 gas and 2 electrons are lost. From here I can write the equivalency condition. 1 mole of Cl2 is equivalent to 2 moles of electron. 1 mole of Cl2 is equivalent to 2 moles of electron. Now an electric current of 100 amps current is given, is passed through molten liquid solution for 5 hours. Time is also given. So charge is given. So from here I can write 96,500 coulomb is equivalent to 2 moles of electron. Sorry, 1 mole of Cl2 means 22.4 liter, right? 22.4 liter at a NTP, because 1 mole of Cl2 will be equivalent to 2 moles of electron means 2 into 96,500 coulomb. What is the charge passed? Q is equals to I into T. Current is 100 amps. To time 5 hours. So 5 into 60 minutes into 60. So we have to take time in seconds and current I in amps. So how much? 5 into 6 into 6, 36. 5 into 36 into
18
100
into 10 power 5.
5 into 36 into 10 power 4. So this will give how many liters? You can try to calculate. 5 into 36 into 10 power 4 divided by into 22.4 divided by 2 into 96,500. These many liters. So 209 liters Faizan says. Check out others. Okay, so like that you can calculate. How long a current of 2 amperes to be passed through a solution of AgNO3 to coat a metal surface of 80 centimeter square with a 5 micrometer thick layer, density of silver is given. Doing the electroplating, you're doing the electroplating, that is silver plating you are doing. Whenever you are doing the electroplating or silver plating or gold plating, the article to be coated is taken as anode or cathode?
Cathode.
Cathode. So whatever the silver coating you have to do. So this is the article, this is a silver. So here the silver is going to be respectively coated. How long a current of 2 amperes, I is equal to 2 amperes, passes the solution of AgNO3. AgNO3 dissociates to give what? Ag plus and NO3 minus. So Ag plus will take up an electron to form Ag. So this was the reaction. How long a current? That means time they are asking. From this I can write the equivalency condition. 1 mole of electron is equivalent to 1 mole of Ag. 1 mole of electron means 96,500 coulomb is equivalent to 1 mole of Ag. 1 mole of silver will have atomic weight of 108 gram. 108 gram. Now, how long a current is passed to a solution of AgNO3 to coat a metal surface of 80 centimeter square? This is a metal surface. Area is 80 centimeter square and 5 micrometer thick layer. So density is equals to like let us say this much is a coating done. This much is a coating done. So that much is a coating done, but we want the weight of the substance, how much is coated, the weight of silver coated. So density is equals to mass by volume. Density of silver is equals to mass of silver coated by volume of silver coated, volume of that particular coating layer. So density of silver is given as how much? 108, 10.8 gram per centimeter cube. That is equals to mass of silver. How much is coated that we have to calculate, divided by volume. So it is coated on a area of 80 centimeter square with a thickness of 5 micrometer. 5 micrometer means what? Thickness is equals to 5 micrometer, 10 power minus 6 meter, right?
Yes.
Yes, sir.
But we have to write in centimeters. So 5 into 10 power minus 6, 1 meter is how much? 100 centimeters, so 10 power minus 4 centimeter. So 5 into 10 power minus 4 centimeter. So I can write therefore mass of silver deposited is equals to 10.8 gram centimeter power minus 3 into 80 into 5 into 10 power minus 4 centimeter cube. Centimeter cube, centimeter power minus 3 gets cancels out. So you get this answer. 5 into 80, 400. 4 into 10 power 2 into 108 into 10 power minus 1 into 10 power minus 4. This is the mass of silver deposited. So mass of silver deposited how much? 4 into 108, 432. 432 into 10 power 2 into 10 power minus 5 is 10 power minus 3. That is mass of silver deposited is equals to 0.432 gram. So this much gram has been deposited. Instead of directly giving the weight of silver deposited, they have said that instead of directly giving the weight of silver deposited, they have said how much part of the metal has been coated, what is the area of cross section of that particular metal, and thickness has been given as well as density is given. So for 108 grams is obtained from this particular charge. So 0.432 gram of silver to be deposited. How much charge has to be passed? 0.432 into 96500 divided by 108. These many coulombs. And we all know Q is equals to I into T. So I can write Q charge 432 into 96.5 divided by 108 is equals to I current. Current of 2 amps is passed. 2 into time. Time in seconds you have to find out. So time T is equal to how much? You do the calculation and let me know. Faizan says 1.93 seconds. Other do the calculation. How it can be 1.93? Check it out like
193.
193, right?
Yes.
Yes. Because 108, 432 means 4 times cancels, 2 ones, 2 times. 193 seconds is the right answer. Okay. Simple, not too complicate. Just they have, instead of giving directly the mass, they have just given the area of cross section of that particular metal which has been coated, and also the thickness of silver layer, and also the density of silver. From that you calculate the mass, write the equivalency condition. From the equivalency condition, try to measure it out. A 250 ml sample of 0.2 molar Cr plus 3 is electrolyzed with a current of 96.5 amps. If the remaining concentration of Cr plus 3 ion is 0.1 molar, the duration of electrolysis is. Assume volume of solution remains constant during electrolysis. So initially we have a beaker, a 250 ml sample of 0.2 molar Cr plus 3. How much is the volume? 250 ml. What is the concentration? 0.2 molar Cr plus 3. 250 ml sample of 0.2 molar Cr plus 3 is electrolyzed. We have done the electrolysis. After electrolysis, what happened? After electrolysis has been done with a current of 96.5 amps. If the remaining concentration of Cr plus 3 is 0.1 molar, 0.1 molar, and assume volume change, like a volume of solution remains constant means volume change is 0. That is again 250 ml only. But in reality, there is some volume change, right? Because of electrolysis, the ions get deposited the respective electrodes. So there will be some volume change in reality, but we have to assume that's what given in the question. Assume the change in volume to be like we can neglect the change in volume. The duration is how much? So they have given concentration and volume. Concentration and volume they have given. We know the formula: concentration is equals to number of moles by volume. Molarity is equals to number of moles by volume. From here I can calculate number of moles is equals to concentration into volume. Because of electrolysis, the concentration changes. Can I calculate the number of moles initially? Can I calculate the number of moles finally? And from that, can I report number of moles has been lost during the electrolysis? Yes or no? I can calculate in that way. So number of moles initially how much? Number of moles initially is equals to initial concentration 0.2 into 250 ml. 250 ml is 1 by 4. 0.2 into 1 by 4. How much is that?
50, sir.
50. In terms of moles, you report like 0.05.
0.05.
0.05. Number of moles final is how much? 0.1 into 1 by 4. That is 0.025. Yes. Therefore, number of moles involved in electrolysis is equals to number of moles initial minus number of moles final. That is 0.05 minus 0.025. That is 0.025 mole. So what was the reaction? Cr plus 3 will take up 3 electron to form chromium. From here I can write 3 moles of electron is equivalent to 1 mole of Cr. So 1 mole of chromium will be equivalent to 3 moles of electron. But actually we are talking about the Cr plus 3 ions, right? So 1 mole of Cr plus 3 also same. 3 mole of electron is equivalent to 1 mole of Cr plus 3. So how many moles of Cr plus 3 has been lost? Therefore 0.025 mole of Cr plus 3 will be equivalent to 0.025 into 3 divided by 1. Yes or no? These many mole of electrons. So that is a charge passed. That is 25 into 3, 75. 75 into 10 power minus 3 mole of electron. So Q is equals to I into T. Again, they were not asking the charge passed, they were asking the time. So Q is equals to I into T. Charge is 75 into 10 power minus 3 is equals to current I. These many moles, 1 mole of electron is 96,000 into 96,500. 96.5 into 10 power 3 is equals to 96.5 into time. 96.5 gets cancels. 10 power minus 3, 10 power 3 gets cancels. So time is equal to 75 seconds. Okay. Chris, if you are taking 250 ml, then you will be calculating respective number of millimoles, not moles, because volume is in ml. If you are taking number of millimoles, then here you have to change. Not an issue. If you want to take 250, you can take 250 also. Then this equation is going to change. 3 moles of electron is equivalent to 1 mole of Cr plus, right? Here you will be getting millimoles instead of moles. Okay, so we are like proper unit conversion has to be done. If you want to take in ml, you can take. If you want to take in ml, you can take, but here while you are substituting, you have to substitute moles. If you have millimoles, you have to convert that again into moles. Right. Four mole of electron were transferred from anode to cathode in an experiment of electrolysis of water. What electrolysis they are asking? The total volume of two dry gases at STP produced will be approximately. Water, if you do the electrolysis at anode, what happens? Oxidation occurs,
Oxygen.
loss of electrons. So 2H2O will be giving O2 gas and 4 H plus ions and 4 electrons. At cathode, reduction occurs. 2H2O will take up 2 electrons to form H2 gas and OH minus 2OH minus ions. Right, from this write the equivalency condition. They are asking the total volume of dry gases. So 1 mole of O2 is equivalent to 4 mole of electron. They have passed how many mole of electron? 4 moles of electrons only. So 1 mole of O2 means 22.4 liters of O2 obtained. Similarly here, 2 moles of electron is equivalent to 1 mole of H2. So 4 moles of electron, because they have passed 4 moles of electron will be equivalent to 2 moles of H2, which is equivalent to 44.8 liters of H2. Therefore, V total is equals to volume of O2 plus volume of H2 in liter, that is equals to 22.4 plus 44.8 liters. 67.2. Yes, 67.2 liter. The passage of current liberates H2 at cathode and Cl2 at anode. The solution is H2 you are getting at cathode and Cl2 at anode. What was the solution?
NaCl aqueous.
Yes or no? If you do the electrolysis of aqueous NaCl, then only you will be getting H2 gas at respect to cathode and Cl2 at anode. So that will be the right option. Okay, so these are the different examples. And one more example, during electrolysis of used calcium hydride, the hydrogen is produced at calcium hydride CaH2. That means you get Ca plus 2 and 2 H minus ions. H minus, not H plus. So 2 H minus will lose 2 electrons to form H2 gas. So H minus hydride ion is negatively charged, that will go towards positively charged electrode. Positively charged electrode is anode. So the hydrogen is produced at anode, not the cathode, because hydride has H minus, not the H plus ions. Okay.
Yes.
The electrolysis of aqueous Cu copper sulfate decreases or causes what? Decreases or increases pH or no change. CuSO4 gives Cu plus 2 electrons. At cathode, what happens? Cathode means negatively charged. So Cu plus 2 and water. CuSO4 gives Cu plus 2 plus SO4 2 minus. So there's a competition between Cu plus 2 and water. Cu plus 2, based on its reduction potential, it will take the 2 electrons to form Cu. At anode, when compared to water and sulfate, water has greater tendency to undergo oxidation. So 2H2 will give O2 and 4H plus 4 electrons. So what happens? More H plus ions are produced. So H plus ions increases the concentration of H plus, thereby decreasing the pH. So option 2. More H plus ions means the solution becomes acidic. So there will be a decrease in the pH. pH is equals to negative logarithm of concentration of H plus. Right. Yes, very good. So then comes the next type of questions. So until now we have seen the concept of electrolysis as well as galvanic cell. And before that galvanic cell, we have also discussed about conductance, equivalent conductance, molar conductance, and relative other concepts. Now we will be looking at the last part of electrochemistry, that is commercial cells. Commercial voltaic cells, like batteries, can be classified as primary and secondary. Two types of batteries are there. Primary batteries cannot be returned to their original state by recharging. So when the reactants are consumed, the battery is dead and must be discarded. Secondary batteries are often called storage batteries or rechargeable batteries. The reactions in these batteries can be reversed, thus the batteries can be recharged. Simple logic is, the primary batteries means use and throw type. You cannot produce the reactants back once they are completely used up. The primary batteries are those type of batteries in which the reactants, once are used up, they are not going to be produced back. Secondary batteries means whenever you are recharging these batteries, the reactants which are used up in the discharging process, they are again produced in the recharging process. The same thing I have explained in the previous class also, like lead storage battery, right? We'll discuss that mechanism now. So primary batteries means use and throw type, where the reactants can't be produced again, whereas secondary batteries are rechargeable, where the reactants can be produced back. Primary cells. So first one is dry cell. The most familiar type of battery is the dry cell, which is a compact of Leclanc cell, known after its discoverer, Leclanc. Like in this cell, the anode consists of zinc container and the cathode is a graphite rod surrounded by MnO2 and carbon. So, and one more important thing which you need to understand is, the reactions happening inside the batteries, they are not very simple like the simple galvanic cell or Daniel cell. They are the complex reactions. So here in the dry cell also, complex reactions are going to happen. So in the cell, the anode consists of zinc container. Like at anode, what happens? At anode, always oxidation occurs. So the zinc container, whatever the zinc container we have, that itself is acting as the anode. So zinc container will act as an anode, means it will undergo oxidation. So Zn will be undergoing oxidation to form Zn plus 2 and 2 electrons are lost. And the cathode is a graphite rod surrounded by powdered manganese dioxide and carbon. So at a cathode, what happens? At a cathode, we have a graphite rod, and that graphite rod is surrounded by MnO2 and a carbon. Like it is a graphite rod surrounded by powdered MnO2 and carbon. And the space between cathode and anode, that is actually occupied by moist NH4Cl and ZnCl2 paste. The moist NH4Cl and ZnCl2, they were actually present between the cathode and anode. So at cathode, what happens means, NH4 plus, the NH4 plus will convert the respective MnO2, like powdered MnO2 and carbon, right? This is actually present between, the NH4Cl is actually present between cathode and anode. NH4 plus will react with MnO2, and always reduction should occur at cathode. So gain of electron, it gains the electron to form a complex like MnOOH. Along with that, ammonia is released. Understand these reactions? At a cathode, what happens? Cathode is a graphite rod. It is an inert rod filled or surrounded by powdered MnO2 and a carbon. That powdered MnO2 and carbon, which is present at the cathode, and the zinc container at the anode, these two are actually separated by the moist NH4Cl. That NH4Cl, from that NH4Cl, the ammonium ion will react with MnO2 and it will gain the electron to form MnOH and NH3. In MnOH, manganese oxygen state is what? +3 state. MnO2, manganese is in +4 state. So at cathode, reduction occurred. And earlier at anode, what happened? Zinc convert to Zn plus 2 and 2 electrons are lost. That Zn plus 2 ions has now a tendency to react with ammonia to form a complex. And based on the sizes of Zn plus 2, it forms a coordination number 4 complex. So the Zn plus 2 will react with ammonia NH3 to form Zn NH3 taken twice whole plus 2. Zn NH3 taken twice, taken 4 times. It is a coordination number 4 complex, right? Zn NH3 taken 4 times whole 2 plus, zinc is in +2 state only, but it is a coordination number 4 complex. Coordination number is equals to 4. So the reactions you can see, they are not as simple as the simple Daniel cell. So in Daniel cell, oxidation occurred, reduction occurred, we can simply write down. The actual reactions happening in the cells which you are using in our day-to-day lives, they are much complex. So NH4 plus will react with MnO2 in the presence of electron to form MnOH plus NH3, where MnOH magnesium plus 3 state, and ammonia released that will react with Zn plus 2 to form a complex ZnNH3 taken for whole 2 plus. All right. These are the reactions happening at a cathode and anode. So whenever using the remote in the dry cell, whatever the electrical energy I need, that electrical energy is actually obtained by the flow of electrons. At anode, whatever the electrons lost, they are going to flow through cathode, right? From the anode to the cathode, the electron flow is happening. That means current electrical energy is produced. With the help of that electrical energy, the whole device is working. Is that clear or not?
Yes, sir.
Okay. So this is the typical dry cell, like positive electrode, steel cover, you can see graphite rod. Graphite rod is actually surrounded by NH4Cl paste. Between zinc anode, this is a zinc anode, this is a graphite rod. Between that, we have all this paste or not, ammonium chloride and MnO2 powder, and ZnCl2 paste is also there. So zinc rod acts as anode, graphite rod with surrounded by powdered MnO2 and carbon is cathode. Between anode and cathode, we have a moist paste of NH4Cl and ZnCl2. Yeah, this is what I'm talking about. The space between electrodes is filled with a moist paste of ammonium chloride and zinc chloride. The electrode reactions are complex, but they can be written approximately as follows. The same reactions. Zn solid converting into Zn plus 2 electrons. MnO2 plus NH4 plus electron forms MnOH plus NH3. Manganese went from +4 to +3 states. In the cathode reaction, manganese is reduced from +4 oxidation state to the +3 state. Ammonia is not liberated as a gas, but it combines with Zn plus 2 to form the complex ZnNH4 taken 4 2 plus. This is the actual complex term. ZnNH3 taken 4 whole 2 plus. Dry cells do not have an indefinite life, as acidic NH4Cl corrodes the zinc container even when not in use. You cannot say, sir, I am not using my device or remote, so why can't the battery be working for lifelong? Because of the corrosion of NH4Cl. Acidic NH4Cl corrodes the zinc container even when not in use. If the zinc is disturbed, obviously oxidation it will not happen, no. Because oxidation of zinc should occur so that the electrons released in that oxidation, they will reach the cathode. That flow of electrons is nothing but electricity, current. So if that zinc itself is disturbed, zinc content is disturbed by the corrosion of acidic NH4Cl, obviously the cell is not going to work anymore. So dry cells will generally have a potential of approximately 1.25 to 1.5 volt. Even though you are not using the dry cell, it will not have indefinite life. And the anodic reactions and cathodic reactions are as follows, as we have studied earlier. Is that clear or not?
Yes,
Yes.
sir.
Yes, right. So that is nothing but your primary battery or a dry cell. Similarly, you can look at the examples of secondary battery, secondary or rechargeable batteries. And the most important secondary cell is the lead storage battery. Lead storage battery, as I was saying about this, we can recharge it. It consists of a lead anode and a grid of lead oxide, a grid of lead packed with lead oxide as cathode. So at anode, what happens? At anode, always oxidation should occur. Like whenever we are using the cell. So we have this type of diagram for the lead storage battery. It consists of lead anode. This is lead which is acting as anode, and the grid of lead packed with lead dioxide as cathode, packed with PbO2 is cathode, and a solution of sulfuric acid 38% by mass or having density 1.3 gram per centimeter cube, that is used as electrolyte. That means H2SO4 is used as an electrolyte, which was actually present between cathode and anode. During discharging, what happens? Discharging means whenever you are using that particular device, whenever you're using, you need the electrical energy, because energy has to be converted from one form to other form. You cannot have infinite source of energy, right? One form of energy has to be converted to other form, so you cannot directly produce energy out of something. So whenever you are using the mobile, you are using the electrical energy. That means the electrical energy is actually produced by the spontaneous oxidation and reduction reactions happening at cathode and anode. So at anode, what happens? At anode, lead is anode, so Pb is converting into Pb plus 2 electrons. Lead salt is converting into Pb plus 2 aqueous, and 2 electrons are lost. The Pb plus 2 will now react with whatever the Pb plus 2 is obtained by the conversion of Pb solid. That Pb plus 2 aqueous will be reacting with H2SO4, because H2SO4 is actually present between anode and cathode. So H2SO4 will provide the sulfate ion SO4 2 minus. Pb plus 2 aqueous will react with the sulfate from H2SO4 to form PbSO4. Pb, yes or no? So look at this conversion. Pb converting into Pb plus 2 electron. Pb plus 2 will react with sulfate to form PbSO4. This is nothing but your solid. What was the ultimate equation happening at anode? Pb plus 2 gets cancels out. Pb solid plus sulfate from H2SO4 is forming PbSO4 solid plus 2 electrons. This was the reaction happening at anode during the discharging process. Understood this process or not, all of you? We have lead as anode and a grid of lead packed with a PbO2 as cathode. At anode, what should happen? Oxidation should occur. During discharging, I am talking. During recharging, the reactions are reversed. During discharging means whenever the device is under use. So lead is converting into Pb plus 2 electrons are released. The Pb plus 2 is reacting with sulfate to form PbSO4 solid. So the complete reaction happening at anode is Pb solid plus SO4 2 minus aqueous gives us to PbSO4 solid plus 2 electrons. Loss of electrons seen, that is oxidation occurred at anode. Similarly at cathode, what happens? At a cathode, at anode, these are the reactions happening. At cathode, what are the reactions happening? At cathode, what is the cathode? PbO2 is your cathode. Yes or no? Cathode is your PbO2, and that PbO2, like lead is in +4 state in the PbO2, and cathode is lead dioxide packed with lead dioxide. That lead dioxide and lead anode, they were actually converted. They are actually separated by H2SO4. So I can say PbO2 will be taking up the H plus ions in the presence of electrons to form respective Pb in the +2 stage. PbO2 plus 4H plus 2 electrons will form Pb plus 2 plus 2 H2O. Pb plus 2 plus 2 H2O. That Pb plus 2 ions which were obtained, they will again react with sulfate SO4 2 minus to form PbSO4, lead sulfate. Ultimately, you have lead ions got cancelled out. You can say PbO2 lead dioxide plus 4H plus sulfate plus 2 electrons is giving PbSO4 solid and 2 H2O. This is a reaction happening at cathode. So what is happening at anode? At anode we have Pb solid plus SO4 2 minus gives rise to PbSO4 plus 2 electrons. At cathode, what happens?
PbO2 plus
Yes, PbO2 plus 4H
4
plus
SO4 2 minus
plus
plus
2
2
electrons
electrons.
is giving PbSO4
PbSO4 plus 2H2O.
2H2O. Very good. So what was the ultimate cell equation? The cell reaction is 2 electron got cancelled out. PbO2 plus PbS 4H plus plus 2SO4 2 minus.
Yes, sir.
4H plus 2SO4 2 minus I can write as 2H2SO4
Yes.
PbS plus PbO2 plus 2H2SO4 is giving 2 PbSO4 plus 2H2O. Right?
Yes, sir.
Yes, very good. So this is a complete reaction happening. Lead plus lead dioxide plus 2H2SO4 is converting into lead sulfate plus 2H2O. That was the ultimate reaction. That is the ultimate cell reaction happening while you are using the lead storage battery. These are the reactions happening at anode. These are the reactions happening at cathode. And anode and cathodic reactions, when you combine, you will get the total cell reaction or net cell reaction. Net cell reaction is lead plus lead dioxide is using up H2S4 to convert to lead sulfate and to H2O. Can I say in the process of using, while you are using the device or in the process of discharging or during discharging, H2SO4 is used up or not?
Yes, sir.
Yes or no? H2SO4 is actually used up in the process of discharging. Recharging means what? Exactly same equations but reversed. Exactly the equations are going to be same, but just they are going to be reversed. Yes or no? Now you have PbSO4 plus 2 electrons gives rise to, like if I reverse this reaction at anode, what happens? PbS plus SO4 2 minus gives rise to PbSO4 plus 2 electron. If I reverse it, PbSO4 plus 2 electron gives rise to PbS plus SO4 2 minus. That is a reaction at anode or cathode then?
Cathode.
Cathode, because there in the reverse reaction electrons are gained. No, gain of electrons happen. That is nothing but it is a cathode. Similarly, you reverse the reaction of cathode, and that will be the new anode now. So cathodic cell reaction and anodic cell reaction, they are going to be reversed, and cathode and anode, they are also going to be reversed. So if you try to reverse the equation, everything is going to be same, but just you have a backward sign. This will be anode. If you have the backward reaction, this will be a cathode. There is a cell reaction. So whenever you are trying to reverse, you are producing H2S4. That means in the process of discharging, H2SO4 is used up. In the process of recharging, recharging means what? Whatever the potential you have been developing here, you apply greater than that potential. Then obviously cell reactions are going to be reversed, reversible cell. In that process, what happens is you will generate the H2SO4. H2SO4 is generated during the recharging while it is used up during the discharging. Right? And that is why it is not advisable to use the device whenever it is under charging, because different types of reactions are happening. Nowadays, we have more advanced batteries like lithium-ion batteries, and the recent Nobel Prize also went to the lithium-ion batteries in the chemistry, like 2021 or 20, like 2 years back, 21 or 20, I don't remember exactly. So that is of great use. And now researchers are also in a way to produce a battery where once it is recharged for like 24 hours, there is no discharging happening even for lifetime. So you can use it for lifetime. The MIT researchers are doing it. Might be thinking the future might be even more flexible, but again, we have to save our environment while developing the respective batteries as well. Right? We have seen the environmental chemistry also. Whatever the batteries we are producing, whatever the electrical energy we are producing, all these, they are causing different types of dust, and ozone layer is disturbed, particulate pollutants, gaseous pollutants, ozone layer disturbance, global warming. All these are side effects which has to be controlled. Okay. Right. The same equations, whatever I have explained, you can see that in the slides now. When the cell is discharging, it operates as a voltaic cell. And one more important thing, whenever you are discharging, whenever you're using the device, the cell is operating as a voltaic cell. That is, due to spontaneous oxidation and reduction reactions, you are producing the electrical energy. But whenever you are recharging it, due to external electrical energy, chemical reactions are done. it is acting as a electrolytic cell. Whenever you are using the mobile or the device is actually acting as a voltaic cell. Whenever you are recharging it due to external electrical energy, the chemical reactions are done. It is acting as an electrolytic cell. There was a difference when you are discharging. When you are discharging, that is actually acting as a voltaic cell. When you are recharging, it will be acting as a electrolytic cell. When the cell discharges, it operates as a voltaic cell. The lead is oxidized to Pb plus 2 and the lead plate acquires a negative charge. So Pb solid is converting into Pb plus 2 electrons. Negative charge means voltaic cell anode is negatively charged, cathode is positively charged. And Pb plus 2 ions combine with sulfate ions of the solution to form insoluble lead sulfate. PbSO4 is going to be forms a solid which is not soluble. Overall reaction Pb solid plus SO4 2 minus converts to lead sulfate plus 2 electrons. The electrons given by lead are used at cathode, that is PbO2 will take up the electron. PbO2 will take up electrons in the presence of H plus ion to form Pb plus 2 and 2 H2O. That Pb plus 2 again react with sulfate ion to form lead sulfate, which is again solid. So this was the ultimate reaction happening at cathode. So overall reaction is, this is the anodic reaction, this is a cathodic reaction, this is a net cell reaction. PbS plus PbO2 plus 2 H2S4 gives rise to PbSO4 plus 2 H2O. That means I can say while you are using while you are discharging the particular device, H2S4 is used up. Is that clear or not? You got the same equations?
Yes, sir.
Yes.
Yes, right. Now let us try to think of the other way. Instead of discharging, let us recharge it. When a potential slightly greater than the potential of battery is applied, the battery can be recharged. During recharging of the cell is actually operating like an electrolytic cell. Why? Because now electrical energy is supplied to it from an external source. That means delta G is positive for that reaction. I cannot keep my cell separately and it will not automatically recharge by itself. It is not spontaneous. The recharging of the device is not spontaneous. Electrical energy has to be supplied, that is delta G has to be positive. Electrical energy is supplied to it from external source. The electrode reactions are reverse of that off during discharge. So at a cathode, what happens? Again, reduction should occur. That means PbSO4 take up 2 electron to form PbS plus sulfate. Like earlier, this was a reaction. The reverse reaction happened at anode. Now the reverse is going to happen at cathode. Similarly, at anode, PbSO4 solid plus 2H2O gives PbO2 solid plus 4H plus sulfate plus 2 electrons. And this was the net cell equation. 2 PbSO4 solid plus 2H2O gives PbS solid plus PbO2 solid plus 2 H2SO4. This was your net cell reaction. In the net cell reaction during recharging process, what happened? H2S4 is produced or not? So whatever the chemical used up in the discharging, that is produced in the recharging. So again, that chemical, because of that particular H2S4, again you can discharge it. Like that, you can be using the device. It is clear that H2S4 is used up during the discharge and produced using recharge. During the recharge, you are producing the H2S4. During discharge, it is used up, and that was a net cell reactions happening in lead storage battery. Is that clear, students?
Yes, sir.
Sir.
Yes, right.
Yes, sir.
Yes, these are the two different types of cells, like primary batteries and secondary batteries. Then we can also have the other type, like fuel cells. Fuel cells means what? Like it is possible to make batteries. Like I want to make a battery in which the reactants are continuously fed. I'm giving the reactants. The reactants are going to be converted to different products, and electrons are going to be transferred. The transfer of electron is nothing but your current. Like we all know Apollo space program, right? In the Apollo space program also, we have used a fuel cell. Like to produce electrical energy in the Apollo space program, we have used a fuel cell. What happens in fuel cell is, so these are the electrical cells that are converting the free energy from the combustion of such fuels like hydrogen, carbon monoxide, the free energy is directly converted to electrical energy. Like I am heating the H2 and O2. Like fuel cell means I'll heat H2. Let us look at the idea. Fuel cell, it is possible to make batteries in which reactants are continuously fed to the electrodes. Electrical cells that are designated to convert the free energy from the combustion of fuels such as hydrogen, carbon monoxide or methane directly into electrical energy, they are called as fuel cells. Like we have hydrogen, H2. H2 is going to be converting into respect to 2H plus and 2 electrons are lost. H2 is going to be converted to respect to H plus and 2 electrons are lost. And O2, O2 will take up 2 electrons to form O2 minus ion. Like if I want to, like O2 means 2 oxygens are there. So if I want to produce O2 minus ion, I'll be taking 4 electrons. I require 4 electrons. O2 plus 4 electrons will form 2 oxygen in the 2 minus state. So to take up 2 electrons, you should get 2H2 gives rise to 4H plus 4 electron. 2H2 will give, because H2 gives 2H plus 2 electron means 4H2, 2H2 will give 4H plus 4 electron. O2 take up the 4 electron to form 2 O2 minus. 4, whenever I try to add 4 electron gets cancels out. So you can write 2H2 plus O2 is converted into 4H plus and 2 O2 minus, that is nothing but 2H2. Like H2 and O2, because of H2 and O2, by supplying hydrogen and oxygen, the hydrogen has been converted to H plus ions, where electron has been lost. That electron lost is now given to or taken by oxygen to form O2 minus ions. That O2 minus ion will react with H plus ion to form H2O. In the total process, what happened is 2 things I can say. First is I produced water. I have produced water from hydrogen gas and oxygen gas. Second is, in the process of production of water, the electron transfer has been occurred. Electrons from the H2 has been transferred to O2. Flow of electrons nothing but current. Current is produced. Water, we are not doing this reaction to produce water. We don't need to produce water by breaking the strong bond between 2 hydrogen atoms and strong bond between 2 oxygen atoms. We have many other sources of water. We are actually doing this reaction to form or to make the transfer of electron from anode to cathode where electrical energy has been produced. But in that reaction, H2O is also produced in the vapor state because the temperature has to be high here. The bond between 2 hydrogen atoms has been broken. The temperature has to be high. Oxygen atoms has been broken. The temperature has to be high. So whatever the H2O you are getting, that will be in the vapor state. We can condense back that H2O and the astronauts can use that H2O also. That is what the water vapors produced were condensed and also added to the drinking water supply for astronauts. That is the pure water, right? H2O vapor. We are condensing back the H2O vapor means it is almost pure water and that can be again added to the purifier and the astronauts can use them. That means it is possible to make a battery in which reactants are fed continuously. We have to supply H2 gas and O2 gas continuously. If we stop the supply of H2 or O2, then the transfer of electrons stops, then the electrical energy will not be there. Reactants are fed continuously to the electrodes. Electrical cells that are designated to convert the free energy from the combustion of fuel cells. Directly we are heating it. Because of that heating, directly we can see the transfer of electrons. Direct conversion of free energy into the respective electrical energy is happening. So the efficiency of fuel cell will be high. Generally, if you go to any thermal power plant and inquire about the efficiency, it will be something less than 25%. The efficiency, how much energy we are produced, how much energy we are producing by burning the fuel, fossil fuel, and how much you are converting into electrical energy. If you check it out of 100%, only 25% is a proper conversion. Lot of energy is lost. And it is also causing a lot of environmental issues. But here in the fuel cells, if you think of theoretically, yes, there was no loss, like directly we are heating it, electrons are transferred. So you should think of 100% is a conversion. but technically speaking, there is always some loss. So the efficiency here in fuel cell is something around 60% to 70%, 60-70% efficiency is much more higher. Yes or no? And efficiency, how you can calculate? Efficiency eta you can calculate as whenever you are trying to heat it, whatever the enthalpy change, that is delta H is the total enthalpy change. But how much is converted to the electrical energy? Only the Gibbs free energy. Delta G by delta H into 100. Whenever I heat a particular fuel, delta H is the total enthalpy change involved in that particular heating process. Delta G is the change in Gibbs free energy which has been properly converted into electrical energy. So delta G by delta H into 100, that was the efficiency. Right? Is that clear, students? How the fuel cells work?
Yes.
Yes, sir.
Yes.
Let's look at the animation now. You will get more clarity. So this was the fuel cell animation. This was the fuel in. See, hydrogen I am passing through here. Oxygen I am passing to the other side. I am heating it, right? So that is converting into H plus ions and electrons are lost. Those electrons lost, they were traveling to the circuit. So electrical energy has been produced. And those are gained by O2 minus ions. They form O2 minus and O2 minus take up the H plus to form H2O. This is proton membrane. That is proton exchange membrane. There should be membrane here which should extend the proton because the H plus ions has to reach the other side where O2 minus are there, then only they will form water. Look at the animation how it is. See H2, O2 they are coming. H2 converted to electrons are lost, electrons are flowing. Those electrons are flowing, H plus ions are moving through the proton exchange membrane. Electrons taken by oxygen to form O2 minus, they react with O2 minus to form water. So that water again you can use. Flow of electrons has been done, electrical energy has been produced. And whatever the surplus fuel, I cannot say every molecule of H2 has been converted to H plus ion. Some will be, some may not be converted because that depends upon the velocity of H2 molecules. H2 molecules of moving in this direction, it is a gas, right? As per kinetic theory of gases, they are moving with very high velocities. Some H2 molecules may not be converted to H plus ions. So they are again recycled. Same happens with the O2 also. In the cell shown in the figure, hydrogen and oxygen are bubbled through a porous carbon electrode into concentrated aqueous sodium hydroxide. Catalysts are imported in the electrode and the electrode reactions are as follows. At anode, we have 2H2 plus 2OH minus converting into 2H2O and electrons are lost. The O2 will react with 2H2 and takes up 4 electrons to form 4OH minus. Ultimate or net cell reaction is this one, or you can also go with this equation which I have written. 2H2 will be giving 4H plus 4 electron. Oxygen O2 will take up 4 electron to form 2 O2 minus ions. But this whole reactions are happening in the presence of concentrated NaOH, right? That's why the equations have been written differently. In the cell shown in the figure, hydrogen and oxygen are bubbled through porous carbon electrode into concentrated aqueous sodium hydroxide. So that NaOH is also there. OH minus ions also used for the conversion of H2 to H2 and electrons are lost, as well as O2 to OH minus in the presence of electrons. This was the net cell equation. This was the net cell equation. And this cell runs continuously as long as the reactants are supplied. If you stop the reactant like H2 gas or O2 gas, if you stop, again the electrical energy cannot be produced. Since the fuel cells convert the energy of fuel directly into electrical energy, the fuel we are heating it, flow of electrons happening. So directly, whatever the heat you are giving, because of that heat, the H plus ions along with that electrons are producing. Those electrons are directly flowing. You are directly converting the energy of fuel into the electrical energy. So they are potentially more efficient than conventional method of generating electricity on large scale by burning hydrogen carbon fuels or by nuclear reactor. Out of all the conventional methods, we have different other methods from thermal power plant, from the water, or from the nuclear power plant, we can also produce electrical energy. When compared to those, This is the most efficient method where the efficiency will be some 60 to 70%. And as I have told you, efficiency how to calculate the change in the Gibbs free energy divided by change in enthalpy into 100. Yeah, that's what efficiency of fuel cell is. Eta is equals to delta G by delta H into 100. Whenever a question has been asked regarding efficiency, you have to always use this, because delta H is the total enthalpy change. Delta G is the decrease in the free energy which has been used to convert that particular energy into the electrical energy. This is the usage. This is the total energy. Delta H is the total energy. Is that clear, students? Is everything clear?
Yes, sir.
Yes, right. And the next part is corrosion. This is the last part of electrochemistry, as I was saying. Corrosion mechanism I have explained you, like corrosion of iron, like rusting of iron. If you remember what happens, rusting of iron. Can anyone brief? We have explained the same mechanism earlier also.
Hydrates of iron is rust.
Yes, like I have explained this corrosion, if you remember in environmental chemistry. Yes or no? So what happens is the iron rod, one point of iron rod acts as a anode that will undergo oxidation. So Fe converts to Fe plus 2 electrons. These electrons are traveling through the rod. O2 will take up these 2 electrons in the presence of H plus ions. From where you get the H plus ions? From the dissolution of carbon dioxide. Yeah, carbon dioxide in water. But in the acidic rain, we have H2SO4, HNO3 as well. If they also dissolve, we have more fastly the conversion of like the reduction happening at the other part, like O2 will take up electron to form water. In the presence of water, the Fe plus 2 ions will convert to Fe plus 3. Along with that, the Fe plus 3 hydrated ferric oxides, they are nothing but your hydrated ferric oxides, that is nothing but your rust. Okay, that was the mechanistic approach. We'll see that. Corrosion means, corrosion is basically an electrochemical phenomena. The rusting of iron, the tarnishing of silver, development of green coating on copper and bronze are some of the example of corrosion. Corrosion causes enormous damage to the building, bridges, ships, and to many other articles made of iron. So most, like hundreds of crores we are losing because of this corrosion every year. Either we are using to coat the iron rods in the process of painting, or if we don't coat it, we'll directly destroy. We will be ending up with damage of that particular total article or the ship. Okay, ships has to be coated carefully, right? So if not, corrosion happens, it's the biggest problem. So corrosion causes enormous damage to building, bridges, ships, and to many other articles made of iron. Anodic reactions, as I have told you, one part of the rod is acting as anode. So Fe is converting into Fe plus 2 and 2 electrons are lost. From here, if you look at the SRP value, Fe plus 2 to Fe conversion is minus 0.44 volt. That is the standard reduction potential for the Fe. That is Fe plus 2 electron converting into Fe means minus 0.44 volt. This is a reaction happening at anode. What about cathode? At cathode, what happens? Oxygen, like the electrons travel through the rod and they reach the other electrode. O2 will gain 4H plus and 2 electrons will form 2H2O. In the presence of H2O, again Fe plus 2 will be converting. Fe plus 2 will react with H2O, will undergo oxidation to form Fe plus 3 and Fe2O3 dot XH2O. Hydrated ferric oxide is nothing but your rust. These are the simplest reactions. The actual reactions are much more complex, but this is how you can understand the reactions happening in the rusting of iron. Anode, this reaction, cathode reaction. At anode, whatever the Fe plus 2 produced, that will again react with water to form Fe plus 3. In this process, H plus ions are again produced. So you can observe more H plus ions there means more fastly the rusting of iron occurs. So Fe plus 2 reacting with water to form Fe plus 3. In the conversion of Fe plus 2 to Fe plus 3, H plus ions are obtained. Those H plus ions will increase the reduction happening at cathode, thereby increasing the rusting. That means initially it takes a long time for the rusting of iron to occur, but once the rust has been formed, the continuous rust is going to be forming greatly. That is, rate of formation of rust will be higher after the rust has been formed because H plus ions are produced automatically. In corrosion, a metal is oxidized by loss of electrons to oxygen and forms metal oxides. Corrosion of iron, which is commonly known as rusting, occurs in the presence of water and oxygen. Although the chemistry of corrosion is complex, but it is understood that one spot of an iron object, oxidation occurs, and that spot is going to behave as anode. The actual reactions happening in the corrosion are much more complex, but this is how we understand them in a simplest way. Electrons released at anode move through the metal and go to another spot on the metal and reduce the oxygen in the presence of H plus ions. The H plus ions are obtained, which is believed to be available from H2CO3 formed by dissolution of carbon dioxide in water. That is, dissolution of gas in water is studied by Henry's law. From Henry's law, we can understand this. This spot works as a cathode. At cathode, what happens? O2 will take up electrons in the presence of H plus from H2CO3 majorly. In case if we have acid rain, then we have H2SO4, HNO3, which will do this conversion greatly. So for this O2 to 2H2O conversion, the electrode potential, the SRP value is 1.23 volt. That means oxygen has a great tendency to undergo reduction to form H2O. Oxygen has a greater tendency to undergo reduction to form H2O. Here Fe plus 2 ions move through water on the surface of iron object. If water present is saline, it will help more in carrying the current in a miniature cell that formed, and it will enhance the corrosion. That means like iron rod, one spot is acting as anode, the other spot is acting as a cathode. So from this anode to the cathode, electrons has been transferred, right? This will act as a miniature. This will act as some miniature cell. Although I am elongating it, anode I am writing here, cathode I am drawing here. They can be very close. A small miniature cell has been produced, flow of electrons has been done. Fe plus 2 ions move through water on the surface of the iron object. If water present is saline, it will help more in carrying the current in the miniature cell. Why? Because if water is saline, it will be acting as an electrolyte, because of electrolyte, the flow of ions is going to happen easily, and it will help in carrying the current, and thus it will enhance corrosion. The overall reaction of miniature cell is sum of cathode and anodic reactions. What is the cathodic reaction? What is the anodic reaction? Fe plus 2 plus 2 electron. Cathodic reaction, O2 plus 4H plus 4 electron is converting into 2H2O. It will form what? 4 electron, like 2 Fe gives rise to 2 Fe plus 2 plus 4 electron gets cancels out. 2 Fe plus O2 plus 4H plus gives us to 2 Fe plus 2 plus 2H2O. And for this reaction, E of cell is how much? E of cell is 1.23 plus 0.44, because Fe plus 2 to Fe is minus 0.44. Fe to Fe plus 2 is 0.44. So 1 point how much?
1.67.
1.67 volt. So E naught of cell is positive. E naught of cell is positive means delta G naught is negative. Delta G naught is negative means it is spontaneous. That means rusting of iron is spontaneous. Production of Fe plus 2 is spontaneous. Fe plus 2 will react with water now to form Fe plus 3, hydrated Fe plus 3. hydrated ferric oxide is nothing but rust. E naught of cell is positive means delta G is negative, and E naught also you can see 1.67 volt greater, so more tendency for the rusting. The Fe plus 2 ions are further oxidized by atmospheric oxygen to Fe plus 3 as Fe2O3 and comes out as rust in the form of hydrated iron 3 oxide expressed as Fe2O3 dot XH2O. Fe2O3 dot XH2O is nothing but your respective rust. And if you look at this conversion, 4Fe plus 2 will react with O2 in the presence of H2O to form Fe2O3 and 8H plus. That means conversion of Fe plus 2 to Fe plus 3, Fe plus 2 to Fe plus 3 releases the H plus ions also. The H plus ions, whatever released, they will enhance the rusting of iron more. H plus ions produced in the above reaction help further in rusting. Initially, rusting might be slow, but once the H plus, once the rust is formed, along with that Fe2O3, whatever the H plus is released, they will help further in the process of rusting, because earlier H plus are obtained at cathode only from H2CO3, but now from here also we are getting H plus. Impurities present in iron also enhance rusting by setting a number of miniature cells. Like in the iron, if you have some other metal M, that metal M can also undergo oxidation along with iron, so that will also act as anode. So oxygen will act as cathode. Like that, impurities present will increase the number of cells, thereby increasing the rusting. So rusting of iron takes place whenever we have more impurities, and very pure iron do not rust quickly. Very pure iron means very less number of cells are going to be formed, whereas if you have impurities, because of more number of miniature cells, more will be rusting happening. Very pure iron do not rust quickly. So whenever we are doing any construction, we have to obviously purchase the pure form of iron, not some impure iron, which can be easily disturbed. Is that clear or not?
Yes, sir.
Yes.
Right. Now we have to stop this rusting of iron. How we can stop this?
Galvanization.
Yeah, galvanizing. Like we have to, we can coat it or not? We can coat it. One thing is, corrosion of metal is prevented by applying a protective coating such as grease, paint, bisphenol, or metal coatings on the metal surface. Like metal surface, you can simply coat it. So whenever you're doing the coating, obviously the metal is not directly exposed to oxygen or the H2O, so reactions are going to be stopped. In case of iron, this coating is done in two ways. What are two ways? Electrolysis, electroplating you can do, like chromium, nickel, and cadmium coating you can do, or dipping iron objects in a molten zinc metal. Mostly zinc and tin can be used. Use of zinc coating to protect iron, that is called as galvanization. Very important. Direct questions can also be asked. Use of zinc coating to protect iron. Use of zinc coating to protect iron, that is said to be galvanization. In galvanizing iron, zinc being more reactive than iron, it will serve as anode and is oxidized. So Zn, zinc is going to be oxidized, not the iron. So Fe is not going to be converting into Fe plus 2. For Fe to convert to Fe plus 2, only we have plus 0.44. But Zn to Zn plus 2, we have 0.76. So which has more tendency? Zinc to Zn plus 2. So zinc being more reactive, that will undergo the oxidation. It will not allow the iron to undergo oxidation. So you can do electrolysis using chromium, nickel, or cadmium coating, or you can just place the iron rod in the molten zinc metal, where the zinc coating will be protecting the iron rod. With this process of protecting iron using zinc coating is said to be galvanization. Similarly, we can actually coat with tin also. Here it is important to note that iron does not rust even after zinc coating is broken, which is not true in the case of tin coating. Like if I have taken this as iron rod, this is your iron rod, I have coated with the zinc. Even though the zinc coating is lost, the iron is not going to be undergoing oxidation. Why? Because wherever some zinc is there over some parts, that only has a tendency to undergo oxidation. But I can also protect the iron with the help of tin coating. If I do tin coating, what happens? Tin will be converting into respect to Sn+2. But the electrode potential of tin, if you look and compare it with iron, iron is more reactive when compared to tin. That means whenever the tin coating has been lost, the corrosion will occur. Here it is important to note that iron does not rust even after the zinc coating is broken, which is not true in the case of tin coating over iron. Why? Because iron is more reactive, because Sn to Sn+2 only plus 0.14, Fe to Fe+2 plus 0.44, because iron is more reactive. Iron is more reactive than tin, and thus if a tin coating is broken, rusting occurs. Is that clear?
Yes, sir.
So,
Right. So these are the different cases. So this is what, now if coating is broken, the iron is exposed, and iron being more active than copper and tin is corroded. Whenever you coat with copper or tin, iron being more active than copper and tin, it is now corroded, because whenever the broking has been done, iron is going to be more reactive and that will be corroded. Here iron corrodes more rapidly than it does in the absence of tin. But tin protects copper in the same way as zinc protects iron. So zinc is going to protect the iron rod. Galvanization. Like how the zinc is going to protect the iron rod, even though the coating of zinc has been lost, the corrosion of iron will not happen. In that same way only, tin protects copper in the same way as zinc protects iron. Tin protects copper in the same way as zinc protects iron. Yes or no? Why? Everything is based on electrode potential values, because E naught of Cu plus 2 to Cu how much? Cu plus 2 to Cu, that is
0.34.
0.34. Yes. E naught of Cu plus 2 to Cu is 0.34. So these are the different concepts of electrochemistry. So electrochemistry, you can think of like 4 perspectives. One is the galvanic cell and all its details. Electrolytic cell, all its details. Electrolysis, quantitative aspect, qualitative aspect. Conductance, molar conductance, equivalent conductance, all the problems. Ionic equilibrium chemistry related problems. Finally, cells, dry cells, lead storage cells, and the fuel cells, as well as corrosion. Okay, so try to read this concept carefully. So let us start with a new chapter named chemical kinetics. Just a second. Rusting of iron is spontaneous or non-spontaneous?
Spontaneous.
Spontaneous.
So delta G is negative or positive?
Negative.
negative.
Delta G is negative. So delta G is negative. Rusting of iron is spontaneous. So that means rusting of iron will occur automatically by itself. So thermodynamics predicts that rusting of iron is spontaneous. That's it. But rusting of iron, is it instantaneous? If I bought iron rod now, will the rusting happens tomorrow?
No, sir.
No.
So,
So rusting of iron is spontaneous according to thermodynamics, but how much time it will take for the rusting of iron to occur, that has not explained, or not that information is not given in the thermodynamics. So thermodynamics only talks about the spontaneity of the chemical reaction. It gives no idea regarding how fast or how slow the reaction occurs. So there are three aspects of a chemical reaction if you think carefully. One is the whether the reaction will occur or not. Whether the reaction will occur or not, that information is actually given by thermodynamics based on the delta G values. If the reaction occurs at a what rate, or up to what extent the reaction occurs, that is given by equilibrium, chemical and ionic equilibrium. We have seen a lot of discussion in the chemical and ionic equilibrium as well. If we know the reaction occurs, if we know up to what extent the reaction occurs, then comes at what rate the reaction occurs, which has been studied in chemical kinetics. So chemical kinetics explains about the rate of chemical reaction, at what rate or at what speed the chemical reaction occurs, right? So what all focuses we will cover in chemical kinetics? Like chemical kinetics focus on what and how is it related to our life? Like which parameters decide as to how rapidly your food gets spoiled? So the spoilage of food is due to some chemical reaction. What is that rate of chemical reaction? We should know. Like if I prepare rice and all, it will last for hardly 1 day or 2 days. Hardly 1 day without any refrigerator. Not even 1 day sometimes. Depends on the outside temperature. If I prepare some pickle, it will last for some months. So there was some chemical reaction happening. There were some antioxidants. Yes or no? So a lot of things are there which are actually controlling that particular chemical reaction of the spoilage of food. So there is some rate. So we have to understand the rate of any particular chemical reaction. How to design a rapidly setting material for dental filling? So if we are going with dental filling, there you have to keep some filling material in the respective tooth which got spoiled. And if that filling and setting, like whatever the material which has to be filled, that will be in the molten state initially, like it will be in the flowing state, in the state of flow. If it is in the state of flow for longer time, is it useful? No. It has to immediately become hard. Like immediately means not instantly, but within some half an hour and all. So that dental filling material, it should also be converting, it should also be setting in a specific time. Again, rate of the reaction comes into scenario. Rate of reaction has a greater impact in our life. We have to know the reaction occurs, the mechanism, everything is fine, but how fast the reaction occurs, that has a greater role, right? If I am doing any reaction, I don't know whether the reaction is going to catalyze or not, whether the specific substance I have added that will catalyze the reaction or not, or it will affect the rate or not, then there is no point of understanding or completing our study. So what controls the rate at which the fuel burns in auto engine? Again, the rate of reaction comes into scenario. So we are indirectly depending upon chemical kinetics every day. We have to know at what rate that reaction occurs. So chemical kinetics is a branch of physical chemistry which deals with the study of rates of reactions, the mechanism by which the reaction proceeds, and factors affecting the rate of reaction. Different factors which are going to affect the rate of reaction, those also taken into account. So it is a branch of physical chemistry which deals with the study of rates of reactions, mechanism by which the reactions proceed, and the factors affecting the rate of reaction. And how is it different from thermodynamics? Thermodynamics only talks about spontaneity. It gives information only about spontaneity. Thermodynamics is all about feasibility of any process, whereas chemical kinetics tells about the rate of the reaction. Thermodynamics is all about feasibility of any process, whereas chemical kinetics tells about the rate of reaction. Like very slowly, diamond can also be converted into respect to carbon. That is a very slow process. That means diamond does not exist forever. it will slowly convert into other allotropic form of carbon. So based on the rates of reactions, all the chemical reactions, whatever we know, they have been classified into 3 types. What are those 3 types? Very fast, very slow, and moderate. Like we have 2 types of chemical reaction based on the extent of reaction: irreversible, reversible. Similarly, based on the rate at which the reaction occurs, we have 3 types: very fast reaction, very slow reactions, and moderate reactions. Acid-base reactions generally are very fast. Rusting of iron, very slow. Many reactions are there in the moderate reactions. On the basis of rate, chemical reactions are broadly divided into 3 categories: very fast or instantaneous, very slow, moderate or slow. Very fast or instantaneous reactions, these reactions take up to 10 power minus 14 to 10 power minus 16 seconds for the completion. You can just imagine the timeline: 10 power minus 14 to 10 power minus 16 seconds. In that time interval only the reaction is done. Generally, these reactions involve ionic species and known as ionic reactions, and they are known as ionic reactions. It is almost impossible to determine the rate of these reactions, because 10 power minus 14 seconds is how we can decide whether the reaction has been done or not. It is not possible to study the kinetics of such reactions. As soon as you mix them, the reaction is done. Okay, it seems to be an instant of time. Example, like strong acid, strong base, HCl and NaOH if you add, Na plus and H2O, NaCl and H2O are going to form. That means the H plus ions and OH minus ions have a greater tendency to react with each other to form H2O. And we all know the dissociation of H2O to H plus and OH minus will be very, very slow. AgNO3 and NaCl, whenever you try to add silver nitrate and NaCl, you form AgCl and NaNO3. Ag plus NO3 minus, Na plus Cl minus, AgCl, white PPT is going to be formed immediately. Whenever you add strong acid, strong base, you get NaCl and water. Similarly, precipitation of AgCl, whenever AgNO3 and NaCl are added, that is also very fast. You can try to add AgNO3 to respect to NaCl, and you can easily see the AgCl molecules. That is, white PPT is going to be formed immediately. So that is a very fast or instantaneous reactions. Similarly, let us look at a very slow reaction. Very slow means generally the example as we have discussed now, rusting of iron, that you can take into account. These reactions proceed very slowly, may take days or months to show any measurable change at room temperature. And is it useful to study the kinetics of such reactions?
No, sir.
No, again, because it is taking the months for seeing the change. We have to again stop that particular rusting of iron by studying the corrosion and all, the chemical reaction, corrosion, coating, and we have done. But it is not possible or not easy to study the rate of very slow reactions like rusting of iron. Reaction between H2 and O2 to form H2O, is that spontaneous? H2 plus O2 is converted into H2O. Why it is not spontaneous? At ordinary temperature, why this reaction will not happen?
Entropy is decreasing because liquid is formed.
Okay, there is no reaction where entropy is decreasing. If I consider the adsorption in the process of adsorption, delta S of system, if you consider, delta S of gas is decreasing or not?
Yes.
That's okay. So here we can easily say that between the hydrogen, 2 hydrogen atoms and between 2 oxygen atoms, the bonds are stronger. So those bonds cannot be automatically broken to form H2O. And also entropy is decreasing. That is also a factor where you can say the reaction between H2 and O2 to form H2O at ordinary temperature, in absence of catalyst, that is not going to happen easily. Moderate or slow reactions. This type of reaction proceed with measurable rates at normal temperature, and we can measure the rates of these reactions easily. So these are the reactions whose kinetics we are going to study in our 12th standard. So mostly these reactions are molecular in nature. Like if you look at the decomposition of H2O2, decomposition of N2O5, these are the examples of these moderate reactions. The kinetics of these reactions will be studied. Okay, is the first classification clear or not? Very fast, very slow, and moderate reactions.
Yes, sir.
Yes.
Yes.
Yes, right. So let us stop our discussion here. Next class we'll be continuing with the details of rate of reaction. What is rates? How to define rate? What is rate of appearance, disappearance, and different other factors as well. Thank you all, everyone. Bye.
Thank you,
Thank
sir.
Thank you.